Welcome again to the Radios Experimental Math Seminars. Today's speaker is our own alumni, Eric Rowland, who joined with Jason Wu. We'll talk about combinatorial structure behind Sinkhorn limits. As usual, please unmute yourself unless you have any questions or comments. Thank you. Go ahead.
Thanks. Feel free to ask questions throughout. So this is joint work with Jason Wu, who was a high school student when we did most of this work and who is now an undergraduate at Cornell. And for the first part of the talk, I'll talk to you about Sinkhorn limits. And then in the second part, we'll see some combinatorial structure that we discovered behind Sinkhorn limits. So what is a Sinkhorn limit? So here's the goal. You start with a square matrix with positive entries, and you want to turn it into a close, whatever that means, doubly stochastic matrix of the same size. So doubly stochastic means that the row sums and the column sums are all one, and close is of some vague notion that we're going to leave undefined for the moment. One way to do this is to think of, so for example, we have this 2 by 2 matrix. We could think of this 2 by 2 matrix as a point in R4, right? And we could think of this as a point in R4 and say, okay, well, let me look at the set of all doubly stochastic matrices also as points in R4, and I could ask literally about the closest doubly stochastic matrix to this matrix as in Euclidean space. That would be one way to answer this question. Historically, that's not the way that a lot of people answered the question, though. And I think what happened was that requires like a level of mathematical sophistication to think of a 2 by 2 matrix as a point in R4. A much more naive way of taking a matrix and getting its row sums and column sums to be what you want is to just naively say, well, let's look at the row sums. The row sum of this first row is 5. And I want it to be 1. So what can I do? I can divide the entries by 5. The top entries, and the entries in the bottom sum up to 3, so I can divide those entries by 3. So by scaling the rows, immediately I have the row sums that I want. So now the rows add up to 1. And then we just need to fix the column sums. We can fix the column sums by doing the same thing, just by scaling each column so that the column sums add up to 1. But by doing that, we broke the row sums. So now the row sums are no longer 1. So what do we have to do? We have to go back and scale the rows again. And now we broke the columns again. So now we have to scale the columns. But if you keep doing this, scaling rows and columns, what you get is that this process actually converges to something. And it's called the Sinkhorn limit is what it converges to. So this 2 by 2 matrix, we say, is the Sinkhorn limit of this matrix for 1, 2, 1. And this goes back to at least 1964. It actually goes back earlier than that. But Sinkhorn was the one who at least claimed to establish that this limit exists for square matrices with positive entries. And in this case, we can actually, maybe you can recognize these numbers. This 0.414 kind of looks like the square root of 2. And in fact, this is a pretty good guess for the exact values of these numbers in the Sinkhorn limit. It turns out that Sinkhorn limits have been rediscovered, not just Sinkhorn limits, but this iterative scaling process has been rediscovered a bunch of different times. Maybe I'll go through these first. Just in predicting telephone traffic, transportation science, economics, image processing, operations research, and most recently machine learning. So this seems to be a natural thing that people, when trying to solve this problem of getting a doubly stochastic matrix that's closer to the original matrix that somehow preserves information about the original matrix, this is a thing that people have gone to many times. Most of these I don't know anything about. The predicting telephone traffic from this paper from the 1930s by Krauthoff. This I read carefully enough to understand what was going on. So it's actually pretty interesting. It's in Dutch, but there's an English translation. I made a YouTube video about it a few months ago where I talk about this in detail. But there are also applications in computer science if you're trying to numerically solve a system of linear equations. The Sinkhorn limit can be used to precondition the linear system to improve numerical stability.
So they gave it a different name. Sinkhorn came later, right?
Yeah, Sinkhorn. So Sinkhorn wasn't aware of Krautoff's work or all these other people's work. So it was rediscovered many times in all these different applications.
So
And so for a while,
1937 was the first time it showed up, as far as you
yeah,
know?
as far as anyone knows, as far as I know, yeah, 1937 was the first time the scaling process showed up. Um, And there's this amazing 100-page survey article from 2016 that's on the arXiv that covers the entire history of Sinkhorn-related results and all sorts of generalizations and abstractions. And so I refer you to that for much more information. But it has applications in computer science. Bauman Kalantari in the computer science department at Rutgers even has written papers on the Sinkhorn limit, studying the convergence of the algorithm, and Avi Wigderson and other authors have been interested in efficient algorithms for computing the Sinkhorn limit. So this is kind of a big area that I knew nothing about until a few years ago. But for this talk, we're not going to need any of that. For all these applications, the people were interested in numeric Sinkhorn limits, computing Sinkhorn limits numerically. So using this scaling rows and columns method. But from a mathematical perspective, we could ask, what are the exact entries of the Sinkhorn limit? So that's what we're going to focus on in this talk. Not anything about convergence or numerics. We want to know what the exact values of the entries of the Sinkhorn limit are. So here's our notation that we'll use for the Sinkhorn limit. We already saw this example. The Sinkhorn limit of 4121 is this matrix. And Mel Nathanson in 2020, posted in 2019, but it was published in 2020, identified the Sinkhorn limit for a general 2x2 matrix with positive entries. So this is his result. The Sinkhorn limit of ABCD is the square root of AD, square root of BC, square root of BC, square root of AD, and then you divide all the entries by this quantity.
Was that Mel?
Yeah,
Nathanson? Yeah.
Mel Nathanson, yep.
Ah.
And one thing that you see as a consequence, at least for 2x2 matrices, is the entries are algebraic, which is not, I think, obvious. Well, it's not obvious when you're just presented with the question of what are the entries, because they arise as a limiting process, and so you don't necessarily expect algebraic numbers to pop out from a limiting process. But for 2x2 matrices, they are algebraic, and we'll see that they continue to be algebraic for larger matrices as well. And in particular, that the top left entry, which is this quadratic divided by the sum of quadratics, it's actually another quadratic itself. It satisfies this degree 2 equation. And the reason I wrote this equation here is because as we go up, the degrees of the algebraic numbers are also going to go up, and at some point we won't be able to have nice closed forms for them. We'll have to write out polynomial equations for them instead. So for 3x3 matrices, for symmetric 3x3 matrices, this is from a paper of Ekhad and Zeilberger. The top left entry of the Sinkhorn limit of a symmetric 3x3 matrix with these entries is given by this. So this is a degree 4 equation with these fairly complicated coefficients. And Ekhad computed these using Grosvenor bases, not just for the top left entry, but for all 9 entries, or I guess all 6 entries, since it's a symmetric matrix. But for a general 3x3 matrix, the answer was not known. So for a non-symmetric 3x3 matrix, you can do this row and column scaling and compute the Sinkhorn limit approximately, but we didn't know what these numbers were. A pretty good guess is that they are algebraic, since we've been seeing algebraic numbers come up in other contexts so far. So we might assume that they're algebraic. How can we guess, for example, what this top left entry is? One way to do that is to compute it to a high precision, which we can do by starting out with the original matrix and pretending that this is 2.00000, to some large precision, and then start doing your row and scaling operations. And so you end up with high precision approximation to the Sinkhorn limit. And then we have to guess a degree. I think if Ekhad and Zeilberger hadn't written their paper about symmetric 3x3 matrices, if we had just had Nathanson's result for 2x2 matrices, that the entries satisfied quadratic equations, I think a natural guess for 3x3 matrices is that they satisfy cubic equations. Of course, that's probably not going to work out because we know when we symmetrize from Ekhad and Zeilberger's result, the degree is at least 4. But if you guess that the degree is 3, what you can do is use an integer relation algorithm such as PSLQ to find a likely polynomial. So if we want to know, if we think this is an algebraic number of degree 3, we can look for an integer relation between x cubed, x squared, x, and 1, and that will give us a candidate polynomial for this number. When you do that, though, with this many digits, you get garbage. You get coefficients, but they're very large. So what we have to do is increase the degree. So maybe it doesn't satisfy a degree 3 equation. Maybe it satisfies a degree 4 equation. But you still get garbage. And when you increase the degree to 5, you still get garbage. And when you increase the degree to 6, you get this polynomial, which looks like garbage, but is actually not garbage. So if you use even more digits than this approximation to the top left entry here, this polynomial doesn't change. And so this seems to be the actual true representation or description of the top left entry of this Sinkhorn limit.
Pretty amazing.
It's amazing. So why is it these particular numbers? Do we have some formula or some way
So this is less garbage. This degree 5 is probably
this is less garbage than degree 5.
Okay.
So I had a couple of high school students before Jason started working on this with me. A couple of high school students worked on this in the summer of 2019. Hofstra has a summer science research program, and this was their project, to take matrices with integer entries, positive integer entries, numerically compute approximations to the Sinkhorn limit, and then use PSLQ to guess polynomials that they satisfy and see if they could figure out some general pattern to the degrees of the coefficients, if not the degrees of the polynomials, if not the actual coefficients. And so their conjecture is that for 3x3 matrices, the entries of the Sinkhorn limit have a degree at most 6. So this is as complex as it's going to get. So this was a conjecture until Jason and I started working on this. And I just want to pause here to mention that if we're looking at general matrices, it's actually enough to just describe the top left entry. That's why I've been kind of focusing on the top left entry. Because if we know one of the entries of the Sinkhorn limit as a function of all of the entries of A, then in fact we know them all. And that's because when you're iteratively scaling rows and columns, that process doesn't care about the order of the rows, right? If you change the orders of the rows and scale the rows, you're still doing the same computation you did before, just in a different order. And same thing with the columns. So there's a lot of symmetry inherent in this matrix scaling, row and column scaling process. And because of that, if you know one of the entries of the Sinkhorn limit as a function of the entries of your original matrix, you actually know them all just by permuting the entries according to rows, permuting the rows and columns in the appropriate way. So we'll just focus on the top left entry. Here's an example of this just to make it more concrete. So suppose this is going back to Nathanson's result. Suppose that Nathanson only proved that the top left entry of the Sinkhorn limit of a 2x2 matrix is this. Well, by permuting the two rows and then using this same formula to get the top left entry of this Sinkhorn limit, right? So what would that be? Instead of square root of AD, we would have the square root of CB in the numerator. And then here we would have the square root of CB, and then the square root of, instead of BC, we would have the square root of DA. Since we've swapped the two rows to get from here to here, the top left entry of this Sinkhorn limit is going to be the bottom left entry of this Sinkhorn limit. And if we swap the columns, then we will get these other two entries. So really, you just need the top left entry, or any other entry as a function of the entries of A, and you'll get them all. Okay, so for 3x3 matrices, let's focus on the top left entry of the Sinkhorn limit. Can we compute it in general? And we can set up a system of linear equations, and this is what, not linear equations, system of equations, which will turn out to be a system of polynomial equations. And this is what Ekhad and Zeilberger did. So if we set up this matrix equation, this is the matrix we're given, A. This is the Sinkhorn limit that we don't know. Every time we scale the rows, that's like multiplying by a diagonal matrix on the left. And every time we scale the columns, that's like multiplying by a diagonal matrix on the right. So if we're scaling the rows and scaling the columns and scaling the rows and scaling the columns, basically we're accumulating a bunch of matrices getting multiplied on the left and a bunch of matrices getting multiplied on the right. And if you multiply all those matrices together, all the ones on the left together and all the ones on the right together, it turns out that product converges. And so there's a single diagonal matrix R that you're going to multiply on the left by to get from A to the Sinkhorn limit, and a single diagonal matrix C that you're going to multiply on the right by to get the Sinkhorn limit. And if we expand out what this matrix equation says, this gives us 9 equations for involving the entries of these 4 matrices. So that's 9 equations. We get additional equations from the condition that the Sinkhorn limit should be a doubly stochastic matrix, right? So the rows and columns of the Sinkhorn limit should add up to 1. So that gives us 6 more equations, 3 for the row sums and 3 for the columns. And the question is, we want to solve this system of equations for the top left entry of the Sinkhorn limit, which is S11, in terms of the original entries of the matrix, the aij's. So we have a total of 15 equations, and we want to eliminate the 14 variables that we don't care about, which are the entries of the diagonal matrices and the 8 entries of the Sinkhorn limit that aren't the top left entry. And if this were a linear system of equations, great, we could use Gaussian elimination. This is not a linear system of equations because we have products here, right? The R's and the C's are being multiplied together in particular. But we can use Grobner bases, which are a generalization of Gaussian elimination to polynomial systems. The thing about Grobner bases, though, is that when you get systems that are sufficiently large, it becomes really unpredictable in practice whether you'll actually be able to compute the solution. And so it was not straightforward to do this, but by messing with the settings, so we were using Mathematica, the default setting for the Grobner basis function in Mathematica did not solve the system of equations in any reasonable amount of time. But if we messed with the settings, we used a different method and different settings, we were able to get the computation to finish. And sure enough, we got a degree 6 equation in the top left entry. Right, so we're trying to turn these 15 equations into a single equation where all the variables we didn't want were eliminated. So we got a degree 6 equation in the top left entry, and the coefficients that I'm going to call B6 through B0 is this mess. So this is the first 2. We'll come back to B6 in a second. Here are B4 and B3. And here are the last 3.
And if it's symmetric, it agrees with what Ekhad and I did?
Yeah, exactly. So if you sort of take the commutative projection of this answer, this degree 6 polynomial actually factors into a degree 4 polynomial, which agrees with Ekhad's output for the symmetric case.
And you actually did it?
Yeah, oh yeah, we actually did it. Yeah, yeah, we actually did it.
Thank you.
Yeah, sorry, not the commutative projection, but the projection where you collapse the general matrix to a symmetric matrix. Yeah, we actually did it and checked. And I think actually the other factor, if I'm remembering correctly, so this degree 6 equation polynomial factors into a quartic, and I think the other term is actually a square. a perfect square. So it's a quartic and a linear linear polynomial squared. So this is a mess. This is a huge formulation. I mean, it's an answer, but it doesn't exactly roll off the tongue, right? So is there a better formulation for all these linear combinations of products of entries of the original matrix? And it turns out there is. So B6 is the first hint of this, right? So B6, and these are in factored form, by the way. So B6, if you look at this for a minute, you'll notice that it's actually a product of determinants. This is the determinant of A, the 3x3 matrix we started with. And these four terms are 2x2 determinants. These four 2x2 determinants. So B6 is the product of 5 minors. A minor is just a word for a determinant that you get by extracting certain rows and columns from a matrix and then taking the determinant of that matrix. So B6 is the product of these 5 minors. It's not just any 5 minors, though. All 5 of these involve the top left entry. Which is probably not a coincidence, right? Because we're looking for a polynomial satisfied by the top left entry, and we're already seeing some dependence or some focus on the top left entry here. So that stands out very, very clearly when you look at these coefficients. The other thing that stands out a little bit, but not quite as much, is if we look at B0. So B0 also factors fairly nicely, and there's a determinant here that doesn't involve A11. And this is something that Jason actually identified, and he said, well, these other 4 factors are also determinants. They're just 1x1 determinants. So here we also kind of have 5 determinants, just like we have 5 determinants here. And I didn't think that was gonna help us get anywhere, but it actually was the key insight into understanding what the structure is of these of all of these coefficients. So B0 is also the product of 5 minors. These minors do not involve the top left entry. More precisely, they don't involve the first row or first column. And then, of course, we have this extra A11 to the 5th here, which is, it's floating around, but there is some uniformity to this. You can kind of explain this away as like a homogeneity factor or something, because we have an A11 to the 4th here and an A11 cubed here. And so this factor kind of appears in all of the coefficients. So we shouldn't put too much emphasis on that. So we have B6 and B0, the leading coefficient and the constant coefficient of this big polynomial. They have very nice structure. To understand the rest, we'd somehow like to interpolate between the 2 endpoints, right? Can we somehow get from B0 to B6 to fill in the structure of these other coefficients? So first, I want to rewrite this in a little bit of a different way. B6 is the product of 5 minors involving A11, but it's also the product of 0 minors involving, so it's the product of 5 minors that do involve A11 and 0 minors that don't. And B0 is a product of 0 minors that do involve A11 and 5 that don't. And now we're closer to sort of interpolating from B0 to B6. The problem is that here we're going from 0 to 5, and we really need another index in there. And so what we ended up deciding to do was multiply each of the coefficients bi by A11. So currently we have B6 as the product of 5 minors involving A11. Well, A11 is its own minor involving A11. So A11 B6 is the product of 6 minors that involve A11. And if we multiply B0 by A11, then we can just increment this. And now we have enough room to sort of interpolate from 0 to 6. So the guess is that A11 BI involves products of I minors that do involve A11 and 6 minus I minors that don't. And that would nicely interpolate between the leading coefficient and the constant coefficient of this equation, of this polynomial. And amazingly, this turned out to work. So of course, there are multiple products of such minors when I is not 0 or 6. And so what do? Well, you look for a linear combination of them. So this is the hardest slide in the talk, just because there's a lot of notation. But we'll first look at this example and then get back to the notation. So this is A11B6. This is the leading coefficient of the polynomial for a 3 by 3 matrix. We've multiplied by A11, so now we have our 6 determinants, or 6 minors. We're going to write those as deltas. And the arguments of the delta are going to tell us which rows and columns we're extracting from the original matrix in order to get that determinant. So in addition to the first row and first column. So to get A11, and that's the definition here. So to get A11, we take 0 rows in addition to the first row and 0 columns in addition to the first column, and extract those. We get a determinant. Here we're taking rows 1 and 2, columns 1 and 2. We get this determinant. Here we're taking rows 1, 2, and 3, and columns 1, 2, and 3, and we get the full determinant. On the other end of the polynomial, this is the constant term that we've multiplied by A11. These are minors that don't involve A11. So here we will explicitly exclude A11, but there's also this extra factor of A11 to the 6th that will kind of distribute among among the determinants. So we'll write these as this. So these are written using gammas. The definition of gamma is here. Here we're extracting, again, rows and columns. Now just taking the determinant, not forcing the first row and first column into the two sets, but then we're also multiplying by A11 to account for this term out front. And so this is the way that we're able to get these two products to look really, really similar, right? So the only thing that changes now is whether it's a delta or a gamma. The 6 specifications, the 6 arguments are all exactly the same. And then we have to take this one step further. So we're going to think of this, this is a product of determinants, but this is going to be just one of the elements in the other coefficients, right? So when we look at B1, for example, we're going to have to take a linear combination of such things. And so I want to wrap this whole product into a single monomial. That's what the M stands for. So we're thinking of this as a monomial in the deltas, and specifying all of the row and column sets that get assigned to delta. And for B0, this is written as M of the empty set because none of the 6 minor specifications get assigned to deltas. They all get assigned, sorry, none of them get assigned to gammas. They all get assigned, no, what I said was right first. None of them get assigned to deltas. They're all ending up in gammas. So this is the definition of M of S. S is going to be a set of these minor specifications. Anything that's in the set gets fed into a delta. Anything that's not in the set gets fed into a gamma. So there'll always be 6 terms, 6 factors in each of these monomials. And the combination of deltas and gammas will depend on how many elements are in the subset. So now let's look at one of the coefficients we haven't pinned down yet. So this is B1. It turns out that you can write this as a linear combination of monomials where just one of the 6 minors is of the delta form and the other 5 are gammas. And that's because we're looking at B1 here. So these 6 coefficients, this is the only way to write this one as a linear combination of these monomials. And then to make things more compact, there's actually a symmetry here. So I want to collapse these four terms into a sum, which we're calling sigma. And that's because these four minors all belong to an equivalence class. And that is the equivalence class of minors that you can turn into each other by permuting rows and columns. So for example, this minor says pick row 2 and column 2. Well, if you permute the second and third row, then now you're picking row 3 and column 2, right? So you can turn these four one-by-one minors into each other by permuting rows and columns. So it's really nice that they ended up having the same coefficient. So this is, again, reflecting the underlying symmetry of the iterative scaling process, where it doesn't care about the row and column order. Okay, so this is the answer. So this is the definition of sigma. Sigma is the sum of the m's, where m of t's, where the t's are go over the equivalence class of s. That you know. So these are minors that you can minor specifications that you can turn into each other by reordering the rows and columns. So this is the compact form for the coefficients of the polynomial equation that is satisfied by the top left entry of the Sinkhorn limit for a 3x3 matrix.
A quick question, Eric.
Yeah.
What are the coefficients representing these -4, -5?
Yeah, so that's a great question, right? So this is what we computed, this is what they are, but of course we want to know, this is a theorem because we got the Grosvenor basis computation and then we were just able to solve for these coefficients from that. So yeah, what do these have any meaning, right? So what we really want to understand is, I think this is in fact the next question, why these particular integer coefficients? Why is it that the coefficient of this is a 1 and that the coefficient of this one is a -1? And we have a pretty good idea, but there's no combinatorial interpretation, which is what we'd really like, but we have something that's very close, and so that's what we'll talk about. But there's also a really nice symmetry, which is that if we look at B1, the coefficients we got were -3, -1, and 1. B5 has the exact same coefficients, -3, -1, and 1. And B2 and B4 also have the same coefficients for -3 and 1, for -3 and 1. So and the symmetry we cannot explain. We don't have any explanation for why the symmetry.
But you got this just by experimenting with the big data.
Yeah. So from those 3 slides of data that was the output of the Grosvenor basis computation, we were able to solve for these coefficients and to write it in this compact form.
So do you use undetermined coefficients once you expected it to be of this?
Yeah, exactly.
Yeah.
And there's a minor wrinkle, which is that in fact these before you write these in their equivalence classes, they don't actually form a basis. I think even in this, anyway, so for B3, the coefficients weren't even unique when we tried to write them as a linear combination of the m's. They only became unique when we used the symmetry of permuting the rows and columns to write them in this form. So that was a persistent problem. We did this for larger matrices also, and we ran into non-uniqueness again. So you can use undetermined coefficients, but you can't always solve for all of the coefficients numerically. Okay, and why degree 6? Why is this degree 6? Well, that has a fairly simple answer, and it's because there are exactly 6 minors that fit in a 2x2 matrix, or in other words, in a 3x3 matrix where you're not allowing the first row and first column. The number of 0x0 minors is 1. That's the one right here. There are 4 1x1 minors, and there's only 1 2x2 minor. And so you can compute this fairly easily for n by n matrices. The number of minors is 2n - 2, choose n - 1. So this is our conjecture for the general degree of the entries of a Sinkhorn limit for a square matrix. An n by n matrix, the entries should have degree at most this, and this is a central binomial coefficient. Maybe I'll just go through these quickly. So for 1x1 matrices, we get degree 1, and indeed this makes sense because if you have a 1x1 matrix with a positive entry and you start scaling the rows and columns, to make them equal to 1, well, you very quickly get the matrix that contains just the entry 1, which satisfies this equation. For 2 by 2 matrices, this is Nathanson's results, and indeed this is degree 2. For 3 by 3 matrices, this is our theorem that has, we'll see that again in another couple slides. But again, what are the integer coefficients? What are the coefficients? Do they have some kind of meaning? And so we tried to run the Grosvenor basis computation for 4 by 4 matrices also. We expected a degree 20 output, but we couldn't get this computation to finish. So what we have to do instead is interpolate from numeric examples. So you can interpolate the polynomial by just randomly generating a bunch of 4 by 4 matrices, iterating the rows and columns till you get approximate fixed points, and then using PSLQ to guess the algebraic numbers that they are. And from that, you can, if you have enough data, you can start building up the coefficients. And so we did this for enough matrices where we actually have an explicit polynomial for the top left entry for a 4 by 4 matrix. But for 5 by 5 matrices, this started to be a problem. So to get more data, what we ended up doing was generalizing to non-square matrices, which have also been looked at in the literature. So this is nothing new. Our particular definition that we used for an m by n matrix is that we scale the rows and columns until we get a fixed point. We want the row sums to be 1, and we require that the column sums are m over n. And so now this kind of breaks the symmetry where the rows are being treated a little differently than the columns, but it specializes when m equals n, it specializes to the standard Sinkhorn limit for a square matrix. And the existence of this limit was established by Sinkhorn in a separate paper 3 years after the first paper. So we still get a limit. And we spent a year and a half of CPU time scaling matrices and running PSLQ. We recognized the 100,000 algebraic numbers. This let us solve for 63,000 coefficients numerically, and an additional 56,000 parameterized by free variables. So this is kind of like an engineering project almost at this point, dealing with all this data. So this is we've seen this already. This is the answer for 3 by 3. What are these coefficients? These integer coefficients seem to be determinants themselves of something that looks like an adjacency matrix. So in the last part of the talk, in the last 10 minutes, I wanna try to give you an idea of what we understand, and we get to look at some pictures here. So let me first remind you what the adjacency matrix of a graph is. So if you have a graph on n vertices, the adjacency matrix is an n by n matrix with entries that are 0 or 1. You get 1 in the entry aij if vertices I and j are connected by an edge to each other, and 0 if they're not. So here we have a graph on 5 vertices. The adjacency matrix is going to be a 5 by 5 matrix. We have a 1 in this entry, for example, because that's row 1 and column 3. Vertices 1 and 3 are connected by an edge. And the adjacency matrix has this nice property in terms of determinants. So if your graph has multiple connected components, then your adjacency matrix is going to be a block diagonal matrix, right? Because you're going to have a bunch of zeros to indicate that one component is not connected to another. And when you have a block diagonal matrix, the determinant is the product of the determinants of the blocks. So the determinant of the adjacency matrix behaves nicely relative to connected components. And what we were seeing is behavior like this. So we were seeing some adjacency type, we were seeing some connected component type structure, and the coefficients were behaving in this way, where when you had two disconnected pieces in the structure, the coefficients seem to be the product of the connected components. And so this led us to suspect through a very, there are many more steps than what I'm describing, but eventually this led us to suspect that we were looking at some kind of determinant of an adjacency matrix. So what is the adjacency matrix that we're looking for? So our integer coefficients are indexed by things that look like this. So again, this is like a set of minor specifications. And our adjacency matrix is going to be a size of S by size of S matrix. So here, this subset has 3 minors in it. That's what this picture is trying to identify, right? So you can imagine this is a 5 by 5 matrix. We don't care what the entries are because we're working in general. We're just interested in how the minors are related to each other. This row 2 and column 2 minor, that's this green 1 by 1 minor here. If we extract rows 2 and 3 and columns 3 and 4, that's this orange 2 by 2, and then this one is this purple one here. Since this is going to be a size of S by size of S matrix, the underlying graph that we're taking the adjacency matrix of should be on the vertex set S. So this should be for this one, it should be a 3 by 3 matrix. So the size of the graph was fairly clear. It's not so clear how do we decide where the edges go? I think it was initially what we expected was that since, for example, these two 2 by 2 minors have their columns are the same, right? They're both columns 3 and 4. So we expected those to kind of be connected. And this 1 by 1 matrix shares a row with this 2 by 2. And so we expected this to be connected, but in fact, that turned out to be wrong. So these are, we ended up falling into the language of calling them links instead of edges because they're sort of 2-dimensional structures. So I'll probably use the word, I'll use the word link instead of edge. But the idea is that we expected these to be connected to each other, at least in pairs, but they're not. So these should be considered unlinked minor specifications, even though they share some rows and columns. And even something like this, where now these are sharing entries with each other, these should also be considered unconnected or unlinked minor specifications. So what should be considered to be linked? So here's an example. This slide will be a family of links. We call these type 1 links. There are 2 types of links, it turns out. So here is a 1 by 1 minor that's a subset of a 2 by 2 minor. These should be connected. On the previous slide, if I just go back, there's a 1 by 1 minor inside of a 3 by 3 minor. Those should not be considered to be connected, but these should be. Similarly, a 2 by 2 minor inside of a 3 by 3 minor should be considered to be connected. A 3 by 3 inside of a 4 by 4 are connected. So type 1 links are links or edges between pairs of minors whose sizes differ by 1, and one is a subset of the other. And this is all empirical, right? So we don't know why this is the rule, but this seems to be the rule. Type 2 links are things like this. So here are 2 1 by 1 minors that share a row, but differ in their columns. These 2 by 2 minors also share their rows. And they have one common column, but one uncommon column, one column that's not in common. These 3 by 3 minors share all their rows and share 2 columns and the differ in 1. So the rule here is that the 2 minors have the same sizes and they differ in exactly 1 row or 1 column. So here are the 2 types of links. Either the sizes differ by 1 and one is a subset of the other, or the sizes are the same and they differ in exactly 1 row or column. And these seem to build the connected components. These determine the connected components. So for example, for this one, how many connected components are there in this picture? Well, we have a 1 by 1 inside of a 2 by 2. So those are connected to each other. But this 2 by 2 is not connected to this orange 2 by 2 because they only share 1 row and 1 column. They don't share both rows or both columns. And it's not connected to this 3 by 3 because it's not a subset. But the orange 2 by 2 is a subset of the 3 by 3. So that those two form a component. So we have two connected components, one with these two minors and one with these two. But if we slide this orange 2 by 2 to the left 1 unit, now we have a single connected component because now the purple 2 by 2 and the orange 2 by 2 satisfy a type 2 link. They're the same sizes and they differ in exactly 1 row. So these are the two rules. Like I said, we don't know where these come from. If anybody has seen anything like this before, we would be really interested to know because it would be nice to connect this to other things in the literature. But we don't have any connections right now.
So for any matrix, you define a graph whose vertices are certain minors?
Yeah, so what we're starting with is, so this is on the level of, we're looking at coefficients in the polynomial equation, and we're trying to, this may answer your question. So the adjacency matrix, there's one more complication, which is that these adjacency matrices we're looking at aren't 0 and 1 matrices. They're built from matrices that look like this. So the diagonal entries are all the same depending on whether they're type 1 links or type 2 links. The off-diagonal entries are somehow weights, either m's or negative n's or negative n's. So these matrices that we're looking at for each, let me just go back to this slide, for each subset of minor specifications, we're looking for the correct adjacency matrix whose determinant will give us the corresponding coefficient in the polynomial equation. So that's what we're doing. And this works very well. So here's an example. You can build this adjacency matrix based on the rules for pairs and the links. And this agrees with values we computed numerically. Unfortunately, it doesn't always agree with values we computed numerically. So for this example, it does not. But if you change the signs of the off-diagonal entries, it does work. So this is the last remaining piece. We don't know what the signs of the off-diagonal entries should be. So there's one little piece of combinatorics that we're missing in order to completely describe the polynomial equation satisfied by a Sinkhorn limit. So this is just a summary slide. I'll focus on this, which is that all of this is conjectural. This is very fitting for an experimental math seminar because we can't prove anything except for the 3 by 3 theorem that we have. But we think that the entries of n by n Sinkhorn limits are algebraic with degree at most this. The polynomial set describing these entries are given by linear combinations of these things, and the coefficients come from determinants of adjacency matrices. So I'll stop there. Thanks very much.
Thank you very much for a great experimental and insightful talk. Any questions? I have a quick question. So the degrees conjecture, how far did you confirm it?
So for 2 by n matrices, the Grosvenor basis computations, actually you can push pretty far. So I think we did 2 by 12 even. I think we got that to work, and so it seems to work. For 3 by n matrices,
and then the degree is the upper bound, right?
Yeah, right. Yeah, so occasionally the polynomial will factor, and so it won't actually be the minimal polynomial. But yeah, for a general symbolic 2 by n matrix, we were able to get the Grosvenor computation to work up to n equals 12.
The reason the Grosvenor computation is so big because you have so many variables. What about if you make everything numeric except for 1 or 2 entries? Then you can probably go further.
Yeah, that's a great question. We haven't tried that.
Anyway, beautiful.
I have a question.
Yeah,
Eric,
go ahead.
earlier you mentioned your YouTube channel. You said it's on YouTube, but you didn't tell people where to go.
Oh, it's youtube.com/ I don't know what it is. If you Google it, you'll find me. The handle is at Eric Rowland. So yeah. Thanks, David.
Anyway, other questions for Eric? Yeah, so this is really, so you almost have a complete description, combinatorial.
Yeah, we're just up to signs, and it's not even the signs of the coefficients, it's the signs of the off-diagonal entries in the matrix. So it's, it's several layers in. Yeah, we almost have a complete description. We just don't know the signs.
And you don't have a full proof yet for 2 by n.
No, we don't have a proof for 2 by n. Oh yeah, thanks, David. That's the link.
Yeah.
So if I understand correctly, for each coefficient, you have a separate graph and you look at its adjacency matrix.
Right. So if we go back to the 3 by 3 theorem, where is this? So for each of these coefficients, there's a separate graph. And the nice thing is that if you fix one of these subsets of minor specifications, but change the size of the matrix, there's some relationship between how the coefficient changes. So all of these, as you change the size of the matrix, all of these polynomials belong to a single family. So that's when I said that the adjacency matrix is really a linear. The entries are linear functions of m and n. That's what I mean as the matrix has size m by n, and when you change m and n, all that changes is the entries change like this.
Yeah, that's really amazing. Okay, any other questions? Well, thanks, Eric, for a great talk.
Yeah, thanks for coming.
Okay, and bye. See you next week. Bye-bye, everybody. Søren, please end this meeting. Thank you. And Eric, please send me the slides.
Okay, will do.
Thank you.